Our last unit's on modern physics. Modern physics started in about 1900 when they started noticing that very strange things happen when they were looking at small things like electrons. And the first place they saw was something called the photoelectric effect. And the description of the photoelectric effect is when light hits a surface and knocks out electrons. In order to knock out the electrons, the light must have enough energy to overcome the energy holding the electron in the surface. And they gave that the name, the work function. So the work function is an amount of energy, the energy holding the electron in. And I put a little note here, it could be any electromagnetic energy, not just light. An example of this is solar cells. Okay, light hits a solar cell, knocks out electrons, and that starts a current flowing. So, the diagram of this might look something like this. I have light coming in, okay, the surface, and let's say the energy of the light is equal to 3 electrons. That's the unit of energy we're going to be using with this. And then the surface has a work function of 4 electron volts. If that happens, no electrons are going to be emitted, because they're being held in by an energy of 4, and we only have an energy of 3. But then if we increase the energy of the wave, let's say we make it 6 electron volts, the work function is the same surface, so the work function is still going to be 4, then electrons are going to come out. Okay? And the kinetic energy of those electrons is just the leftover energy. So the light had 6 to give up, it only took 4 to release it, and the kinetic energy is going to be 2. And if you remember that this is almost always a conservation of energy problem, it's going to make the problems much easier. Now, that seems simple enough, but they found out something very, very strange. Okay, that bright, low frequency light won't knock out electrons. In some cases, but very dim, so very low energy, high frequency, will. And that didn't make any sense. So a diagram of that might look something like this. Okay? So we have bright, low frequency, let's say it's red. The energy of it is 400 EVs. Hits the surface with a work function of 10 EVs, and no electrons come out. Okay, it's kind of strange because it has plenty of energy to overcome the work function, and yet we're not getting electrons. But then, if they use very dim, not a lot of energy, okay, and let's say green, that's a higher frequency. And let's say the energy of this is equal to 13 EVs. The work function is still only 10. So electrons are emitted with a kinetic energy of 3 EVs. And they couldn't figure out why that was happening. Why couldn't the red, which has tons and tons of energy, overcome the work function and knock out electrons? And the explanation came from Albert Einstein. He was building a little bit on the work of Planck. And what he said is that light comes in particles. Called photons. The energy of the photon depends on the frequency. brightness depends on the number of photons. And electrons can only absorb one photon at a time. And this actually explained why the bright red light would knock them out, but the dim green would. Here's why. Okay. So the bright red. Draw the surface. Let's say the work function is equal to 4 EVs. And bright means lots of photons. So red, low frequency, means each photon has kind of low energy. So it might look something like this. Got a whole bunch of photons coming in here. Okay? And the energy of each photon is 3. I wouldn't get any electrons because each one only has 3 and the work function's 4. Even though I have a total of 9 energy, which is greater than the work function, it can only absorb 1 at a time. But if I turn to dim and green, so dim, it's going to have less photons, so maybe only 1 photon, but because it's a higher frequency, green's higher frequency than red, its energy is greater. So let's say the energy is 6 EVs. Work function's still 4, and I get electrons out, I would have a kinetic energy of 2 EVs. So even though there's less total energy, there's only 6 compared to 9, electrons will be released and with the green light. Now, why is the photoelectric effect important? It showed that light can at least sometimes be a particle. Okay. We say that light has a dual nature. Can be a particle or a wave. It actually has to be a wave in order to do diffraction interference. Right, bending behind a barrier, where their amplitude's adding up. Particles don't do that. But in order to explain the photoelectric effect, it has to be a particle.